Good evening to Anantur. So today the group 1 of the Department of Mathematics is going to present on the topic atomic nucleus, its classification and some basic properties. So now let me invite our group member Alan Antony to start the presentation.
Hello friends, good evening. Now let's see some basic concepts about nucleus. In every atom, the positive charge and mass are densely concentrated at the center of the atom, forming its nucleus. The nucleus was discovered by Ernest Rutherford in 1911. It consists of the elementary particles, protons and neutrons, which are commonly known as nucleons. A proton has positive charge of same magnitude as that of electron, and its rest mass is about 1836 times the mass of an electron. A neutron is electrically neutral whose mass is almost equal to the mass of the proton. The radius of the nucleus is smaller than the radius of an atom by a factor of about 10 raised to 4. Volume of a nucleus is about 10 raised to 12 times the volume of the atom. The nucleus was done by Ernest Rutherford through the alpha particle scattering experiment. In 1911, Ernest Rutherford discovered the dense atomic nucleus by bombarding a thin gold sheet with the alpha particles emitted by radium. You can see the figure in the next slide. The conclusions he made after the experiment was that there is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. Revolve around the nucleus in a well-defined orbit. The size of the nucleus is very small compared to the size of an atom. Hence, Rutherford's alpha particle scattering experiment shows the presence of a positively charged nucleus in the atom. Thank you. Now I invite Aleena Jose to continue the presentation. Thank you.
Thank you, Alan. Your presentation was excellent. And now I'm dealing with the topic neutrons and the classification of nucleus. So first of all, neutrons. Neutrons are the constituent of every atomic nucleus except ordinary hydrogen. And it was discovered by James Chadwick in 1932, and he was also awarded a Nobel Prize for that. And it was produced by bombarding beryllium with alpha particles. And so now we can discuss the properties of neutrons. Neutrons has got zero charge, they are electrically neutral, and the rest mass is equal to 1.67493 into 10 raised to minus 27 kilogram. And it has got high penetrating power and low ionization power. Its spin is half, and in free state it is unstable and it decays to electron, proton, and antineutrino. Next is the classification of neutrons. Based on kinetic energy, we can classify the neutrons into two, slow neutrons and fast neutrons. Slow neutrons, their kinetic energy is in the range of 0 to 1000 electron volt, and fast neutrons, kinetic energy is from 0.5 to 10 mega electron volt. Slow electrons, they are in thermal equilibrium with the medium through which they pass, and hence they are called thermal neutrons. And fast neutrons, when they pass through material, slow down by collisions with the nuclei of the material, and they lose a part of their energy. This is a picture of the fast neutrons. Next is the classification of nucleus. So before getting into the classification of nucleus, let's recall some things which we have already learned. That is, we know that a nucleus species is represented by the notation X is Z to A, where Z is the atomic number, which is equal to the number of protons, which is same as the number of electrons, where A is the mass number, which is equal to the total number of protons and neutrons. So the first classification of nucleus, that is the isotopes. Isotopes are atoms of the same element whose nuclei have same atomic number Z, but they differ in their mass number. For example, 1H1, 1H2, and 1H3, they are the three isotopes of hydrogen. So next is isobars. Isobars are atoms of different elements but they are having the same mass number but different atomic number. Example, argon 1840 and calcium 2040. So here we can see that argon and calcium has the same mass number 40, but they differ in their atomic number. Next are isotones. Isotones are atoms of different elements, but they are having equal number of protons. So in the example, we can see calcium, nitrogen, and oxygen. They have got the same number of neutrons, that is 8. Next is isomeric nuclei or isomers. They are nuclei having same atomic and mass number, but they only differ from one another in their nuclear energy states, and they have also a difference in their internal structure. And the difference is in the manner of the radioactive decay, and they are distinguished by their lifetimes. Next is isodiaphers. Isodiaphers are nuclides which have different atomic numbers as well as mass numbers, but they are having the same neutron excess. So what is this neutron excess? Neutron excess is the difference between the number of neutrons and protons in the nucleus. For example, thorium-234 and uranium-238. So in the case of thorium, we can see that number of protons P equal to 90, N equal to 144, and the neutron excess N minus P equal to 54. In the case of uranium, P is equal to 92, N equal to 146, and the neutron excess N minus P equal to 54. So they have the same neutron excess, making them isodiaphers. Next is mirror nuclei. Mirror nuclei are the atoms which have the same mass number A, but their proton and neutron number are interchanged. That is here in the case of beryllium 47 and lithium 37. In the case of beryllium, the number of proton is equal to 4, N equal to 3. While in the case of lithium, P equal to 3, N equal to 4. So it is clearly visible that their proton and neutron number are interchanged, making them a mirror nuclei. So that's all. Thank you. And now let me invite my friend Aleena Binoy to continue the presentation.
Thank you, Aleena. And the presentation was so nice. So far, we have learned about nucleus, its classification, etc. And now I'm going to introduce my topic, that is basic properties of nucleus. So before introducing my topic, I would also like to share some terminologies or some terms that you should keep in mind to follow the following sections. So the first one is atomic number, that is represented by the letter Z, which is the number of protons in nucleus. And the second one is neutron number, that is represented by the letter N, that is the number of neutrons in nucleus. And the third one is mass number A, that is which is the number of nucleons in the nucleus. So these are some terms that you should keep in mind in order to follow our next sections. So next slide, please. So today I'm going to explain or take about the properties of nucleus. Before telling about the properties of nucleus, we have learned what is nucleus, and some facts or some information is given by Aleena. And we all know that nucleus is made up of protons and neutrons, and these protons carry positive charge, neutrons carry no charge. So these are some basic ideas of nucleus. And today I'm going to take three properties, that is nuclear radius, nuclear density, and nuclear force. So first of all, we can move on to nuclear radius. So next slide, please. Okay. Nuclear radius is the distance from the center to the point where the density has decreased to half of its value. And this nuclear radius is of the order 10 raised to minus 13. So simply we can say nuclear radius is the distance from the center to half of, where the density will reduce to half of its value. And next slide, please. So next we are moving to an experiment, that is Geiger-Madsen experiment, and there is a pictorial representation given below. And in this experiment, a narrow beam of alpha particles from the radioactive source was incident on a thin gold foil. And when these alpha particles is incident, the scattering of alpha particles takes place, and it was detected by a detector. And the observations are given of this experiment. Next slide, please. So, from this experiment, they observed that most of the alpha particles just pass through without any deviation. And a few alpha particles were deflected through small angles, and a few alpha particles deviated through large angles. So this was some observation, and this large deflection is possible only if alpha particles collide with heavy and positively charged particles inside the atom. And we said this is positively charged because like charges only repel each other. And this massive positive charge is at the center of the atom, and we call them as nucleus. And only very few alpha particles were rebounded. That means only a few particles were deviated through 180 degree. So this concludes that the nucleus is very small as compared to the volume of the atom. So next slide, please. Okay, so from the observations of this Geiger-Madsen experiment, Rutherford put forward the concept of his atomic model. So the atom consists of a centrally located positively charged nucleus. So the observations or conclusion he came to was the atom consists of a centrally located positively charged nucleus, and the whole mass of an atom is concentrated in the nucleus. Around the nucleus, there is also empty spaces in which these negatively charged electrons are revolving in different orbits. And the total positive charge is equal to total negative charge. Next slide, please. So from above experimental data and observations, we came to a conclusion, or we are getting a derivation or an equation for the radius. So radius is directly proportional to a raised to 1 by 3. That is, r is equal to r naught a raised to 1 by 3. Here r is the nuclear radius, and r0 is equal to constant for all nuclei, and a is the mass number of nucleus. So the equation is r is equal to r naught a raised to 1 by 3. So this is about nuclear radius, and now we can move on to next topic, that is nuclear density. Next slide, please. So nuclear density, in simple ways we can say that nuclear density is the density of nucleus of an atom, or it is the ratio of mass per unit volume inside the nucleus. So it is, since this atomic nucleus carries most of the atomic mass, and this atomic nucleus is very small. When we compare with the entire atom, this atomic nucleus is very small. Since this atomic nucleus carries most of the charges, and this atomic nucleus is very small in comparison to entire atom, the nuclear density will be very high. So a typical nuclear density for a can be approximately calculated from the size of the nucleus and from its mass. So next slide, please. So now we are moving to the formula or derivation of nuclear density. So we are assuming this nucleus as a sphere, and the density is calculated by taking the mass of nucleus over its volume. So first of all, volume is equal to, since we are considering nucleus as a sphere, V is equal to 4 by 3 pi r cube, and V is the volume in meter and R is the nuclear radius in meter. And mass by volume is density. So mass is equal to AM. So here M is the mass of single nucleon and A is the number of nucleons. Next slide, please. Okay, here density is equal to mass by volume, and we are putting R is equal to, we have learned the equation, that is R is equal to R naught a raised to 1 by 3. So we are substituting here, and density is equal to 3m divided by 4 by 3 pi r naught a raised to 1 by 3. And when we assign values, we will get density is equal to around 2.3 into 10 raised to 17 kilogram meter cube. So this is something about nuclear density. So now we can move on to the next section, that is nuclear force. Next slide, please. So nuclear force is a strong attractive force between nucleons in the nucleus that holds the nucleus together. and it is also known as nuclear interaction or strong force, and it binds protons and neutrons into atomic nucleus. And these molecules, we know that molecules are made up of atoms, and there will exist a chemical bindings. And atoms are held together in a molecule. And it is said that the nuclear force is about 10 million times stronger than this chemical binding that holds atoms together in molecules. So now let us consider that a nucleus of atom, except hydrogen, will contain more than one proton. Each proton carries a positive charge. So one question here arises is that why would the nuclei of these atoms stay together? Obviously, the proton must feel a repulsive force from the other neighboring protons. Then also, why would the nucleus of these atoms stay together? Here, the nuclear force is acting here, and the nuclear force is created between nucleons by the exchange of particles called the mesons. So now we can move to the properties of nuclear force. Next slide, please. Okay, properties of nuclear force. So first property is it is attractive in nature but with a repulsive core. So when we have said about our definition of nuclear force, it was said that nuclear force is strong attractive force. So it is attractive, but in repulsive core, that means we have said that when this nucleus is made up of protons and neutrons, and there will be more than one protons, and each proton is positive charge, and like terms or like charges will repel each other. So the protons must feel obviously a repulsive force from the other neighboring protons. So it is attractive in nature, but with a repulsive core. And the next topic is the range of a nuclear force is very short. So at 1 Fermi means it's a femtometer, that is an SI unit of length, that equals to 10 raised to minus 15 m. And okay, at 1 Fermi, the distance between particles in a nucleus is very tiny. At this range, the nuclear force is much stronger than repulsive force. And if the distance is more than 2.5 Fermi, the nuclear force is practically non-existent. Okay, now the third property is the nuclear force is identical for all nucleons. It does not matter if it is a neutron or proton. Once the resistance is taken into consideration, nuclear force affects everything in the same way. And the last and final property is that at a distance of less than 0.7 Fermi, this force becomes repulsive. So this is one of the last and one of the most interesting and last property. So as this repulsive component of the force is what decides the size of the nucleus, the nucleons come closer to each other till the point that the force allows, after which they are not able to come closer because of the repulsive property of the force. So these are some properties of nuclear force, and now I welcome Annu Lukose for further sections.
Thank you, Aleena Binoy. It was very informative section. Now I am going to talk about charge of the nucleus, mass of the nucleus, and nuclear spin. Charge of the nucleus. So as we know, atom consists of tiny nucleus surrounded by moving electrons. Nucleus contains positive nucleus contain protons, which is positively charged, neutrons, which is neutral. Protons, which is positively charged, neutrons, which is neutral, then electrons will be negative charge, that is -1. So it has a charge which is -1, exactly equal and opposite to that of the proton in any complete atom. The proton in the nucleus is precisely equal to the number of electrons orbiting around it. Therefore, we can say that in any atom, number of protons in nucleus is equal to number of electrons orbiting it. Therefore, the total number of charge is equal to 0. Sona. So, however, a nucleus is not a simple collection of protons and neutrons, but they strongly combine with each other through a strong interaction named the nuclear force that is already discussed by Aleena Binoy. So, there are some theories uh, by Albert Einstein's special theory of relativity, in that mass and energy are equivalent and they are expressed as E is equal to mc square. That is, mass multiplied by square of the speed of light. Very small amount of mass may be converted into very large amount of energy and vice versa. Now we are going to talk about mass defect. Next slide. Next slide. So mass defect. What is mass defect? So if two or more particles interact to combine together, then total mass will decrease to be less than the sum of masses of individual particles. The stronger the interaction becomes, they become more tied together. So the more the mass decreases. So this decrease of mass of system is called mass defect. So the difference between the rest mass of a nucleus and the sum of its constituent nucleons is called its mass defect. The formula is del m is equal to z mp plus a minus z mn minus capital Mn. So here del m is mass defect, a is mass number, z is atomic number, small m P is mass of neutrons and capital is mass of nucleus, and small mn is mass of neutron and small mp is mass of proton. Next we are going to talk about spin, nuclear spin. So as we all know, the subparticles are neutrons, protons and electrons. So protons and neutrons, they are having half spin, spin halves. That is, they have intrinsic spin angular moment of their own, and they have orbital angular moment of their own. So they both combine together and will be getting total angular moment. And this total angular moment is represented by L and is called as nuclear spin. So nuclei often act as if they are a single entity with intrinsic angular moment L. Each nuclear, each nuclear spin is a nuclear magnetic moment. So this produces magnetic interaction with the environment. Next slide. So there are certain rules which determine the net spin of the nucleus. They are as follows. First, if number of neutrons and number of protons are both even, nucleus has no spin. That is, number of neutrons and number of protons are actually equal in number and both are even in number. There is no spin. So if number of neutron with number of proton is odd, it is nucleus has a half integral in integer. Sorry. So spin will be 1 by 2, 3 by 2, 5 by 2, etc. So next, third one is if number of neutrons and number of protons is odd, that is, they are having odd numbers, that nucleus has an integer spin. That is 1, 2, 3. So that's all. Now I welcome Sona Sibichan.
Thank you, Annu. The presentation was really nice, and I'm continuing. My topic is binding energy. The binding energy of a nucleus is the energy required to break up a nucleus into its constituent protons and neutrons and to separate them to such a large distance that they may not interact with each other. The equation of binding energy, that is delta E is equal to delta M into C square, where delta E is the binding energy, delta M is the mass defect which was introduced to us by Annu Lukose. The next is binding energy per nucleon. It is the average energy which is required to extract one nucleon from the nucleus. The equation of binding energy per nucleon is delta E by A, where delta E is the binding energy, A is the mass number. The binding energy per nucleon gives a measure of the force which binds the nucleons together inside a nucleus, and it also gives a measure of the stability of the nucleus. Since the greater is the binding energy per nucleon of a nucleus, more stable will be the nucleus. The next is binding energy per curve. Binding energy curve. This is the graph of binding energy per nucleon drawn against mass number A. We can see it is plotted there that binding energy per nucleon in the y-axis and mass number in the x-axis. Next, we comes to know that the binding energy curve reveals so much of things, or it gives us so many informations. They are binding energy per nucleon is really small for light nuclei. For example, the isotopes of hydrogen, that is protium, deuterium, and tritium. The next point is that the mass number ranging from 2 to 20 have maxima with, for the atoms such as helium, carbon, oxygen, indicating higher stability of the nuclei, and it is minima for lithium, boron, and nitrogen, indicating low stability. And the next point is the mass number ranging from 40 to 120. The curve has broad maximum and a peak value corresponding to iron. The next point is that as the mass number increases further, the binding energy per nucleon shows a gradual decrease. This is due to column repulsion between the protons, which makes the heavier nuclei less stable. And the binding energy curve also explains the phenomena of nuclear fission and nuclear fusion. Next, we comes to nuclear magnetic moment. It is a magnetic moment of an atomic nucleus which arises from the spin of protons and neutrons. And then last topic is that packing fraction. Packing fraction of a nucleus is its mass defect per nucleon. The equation of packing fraction of a nucleus is mass defect by mass number, that is delta M by A. If the packing fraction is positive, the nucleus is unstable, and if the packing fraction is negative, then the nucleus is stable. With this, we come to the end of this presentation. Thank you.